So we have multiple forces acting on the object, rotating us in that circle. And as it spins around, we know that there are, well, if we took a snapshot of it, this object really only has a handful of forces. What are they? What are we guaranteed if we're on Earth? We have gravity pulling us down. Good. And tension. That's the other guaranteed force to keep us in this circle. And for us to stay in this circle, was anybody touching those coins when they were rolling around in the circle? Okay. And was my hand like shoving the mouse around? I had to wiggle the string a little just to keep it going, just to counteract friction and air resistance. But for the most part, those are the only two real forces. So, was the mouse moving up or down? Okay. So if the mouse wasn't moving up and it wasn't moving down, we know how strong this upwards pull is. That should equal mg. And we know it's from this tension force, right? So if it's from Ft, we know that this blue line is now a portion of it. Ft, it's adjacent to that angle. Ft cosine, so it's the cosine is equal to gravity. And then we're left over with, this is the only remaining amount. After those two have canceled out, up and downs have canceled out, we're left with that side-to-side amount, which is how it moves in its circle. We're going to call that the net force, or the fact that the net force is acting in a circle. So that's everything we need in our picture, in our diagram, and then we're going to translate that into math terms. We said that Ft cosine theta equals mg, but where that really comes from is the net force in the, we said up and down direction, is equal to 0, right? Not moving up, not moving down, not accelerating. And in our diagram, we have the up arrow, Ft cosine theta, minus mg, right? If we solved for, well, if that equals 0 and we solve for tension, we have Ft equals mg over cosine theta. Wait, I feel like we've done this before, haven't we? Yesterday, when we were talking about ramps and going around a banked curve, we had gravity and we had a normal force. Those were the only two real forces as well. And so right now, if all we have is a downward force and that diagonal pull holding us in this circle pattern, we end up with pretty much the same formula. And, or formulas, because what happens in the x direction? The net force, oh, that's supposed to be an F. The net force in the x direction is how it moves in a circle, right? And so we have the net force in our picture is just the circle, ma, or mv squared over r, and the shape in our picture is, what's that line in our picture up here as a proportion of this triangle? mg, no, ft sine theta. Yeah, we just said the wrong thing. It's okay. Ft sine theta. Alrighty, so let's read the sample problem. We've set it up a pretty good ways. We have a 0.45 meter long string. The ball is set in motion. We have an angle from the vertical, 25 degrees. What's the speed of the ball? So we're looking for this v, speed. Can we just plug this? This is ft solved for it. That's ft right there. Why don't we just substitute? mv squared over r equals mg over cosine theta. That's what we're plugging in for ft times sine theta. What's the next math step? What do you want to do with this? Two things. Sine over cosine is what? Okay, so we have tangent theta. So we have, and we also cancel out mass. Yeah, that's what you said. I could barely hear you. V squared over r equals g tangent theta. I feel like there's something else, but that's it, huh? So if we solve for v, we have v equals gr tan theta. Root, right? There's still a squared, so let's get rid of that squared. Root both sides. We still have a problem. We don't have the radius. Oh, but that's an easy problem to fix because we do have the length of the string equaling 0.45. And I bet you know how to get a radius from there. This is the 25 degrees. It's opposite of it. So L sine theta is equal to the r. Is that true? This is the hypotenuse, yeah. So 0.5 sine r. Go ahead and solve for that now. 0.45 sine 25. Let me know what you got.
0.19.
Right. Okay. So if that's what we have, that's the radius. The reason why I did this is because if I said that this is G L sine theta tangent theta is sine theta tangent theta, multiply into anything special that I can eliminate that. And R is a pretty useful piece of information because we use the radius a whole bunch of times. So maybe it might be helpful to set the radius aside somewhere just so we know. Even though we could move past it without ever solving for the radius itself. Because we could say 9.8 times 0.45 sine 25 tangent 25. Why don't we just put 0.190 right there? 9.8. What's the square root of 9.8 times 0.19 times tangent 25? What'd you get as your final answer?
0.9.
0.9 what?
931.
931?
Yeah, if you round it off, it's 932.
932?
Yeah.
Okay.
Meters per second.
Meters per second. Good. Find the time period of the conical pendulum. Any formulas you want to just throw down to try? I'm down for just writing down formulas. 2 pi r divided by t is our speed. Distance over time, right? We have the speed. We have... Oh, hey, look, there's that radius, right? If we didn't solve for the radius independently, we'd still be doing L sine theta right here. And then we're solving for t. So t equals 2 pi times 0.19 times divided by v 0.932. I think I skipped the pure algebra step of 2 pi r over v equals t. Okay, so if you need that step to get there, I get it. 1.2 8 seconds. If the mass of the metal ball is a 0.2 kilograms, what's the tension of the string? Where did we say Ft equals? We have all those parts. M is now 0.2. G is 9.8 cosine 25 over cosine 25. There's another place where I could plug it in, but it's not as friendly. We could have said, hey, look, mv squared over r sine theta equals ft. That's not as friendly. And we know it's the same thing, right? Maybe. Wait. Okay, never mind. Don't wait. Go ahead and solve it. Equals 2.16. What is that? Units. Newtons. Okay. The only thing that I would double check is that if the mass is 0.2, that my tension in the string, how did I draw it? Should it be greater or less than gravity? Greater than gravity. That's the only thing that I check. Slightly greater than gravity, right? It has to be long enough to match gravity in its vertical direction and be strong enough to be out diagonally there. Okay? All right. That's it for today. What I would say is that there are some problems and a chart to fill in. Those are important components in terms of the way we go about this class.